Hello everybody, welcome to today's tutorials on recycle based problems. We have looked at recycle for systems with reactions and without reactions. We have performed some example problems which were simple. So, today we will solve two problems for tutorials so that we can learn how to approach these recycle problems in a step by step fashion. Let us look at the first problem. The flow chart of a steady state process to recover crystalline potassium chromate from an aqueous solution is shown in the figure. You are asked to calculate the rate of evaporation, the rate of production of crystalline potassium chromate, the feed rate that the evaporator and the crystallizer must be designed to handle, and the recycle ratio. So, have a look at this flow chart. What you see here is 4500 kilograms per hour of 33.3% potassium chromate solution entering as fresh feed. So, this gets mixed with the recycle stream which is the filtrate and it forms a gross feed or the total feed. So, this would be the feed rate to which the evaporator must be designed to handle. So, we need to calculate this particular stream and we also need to calculate this stream which is the feed rate to the crystallizer and filter, which is the what the crystallizer needs to be designed for. So, in addition to these things we also need to calculate the rate of evaporation and the rate of production of crystalline potassium chromate, which would be this, and with all this we also need to calculate the recycle ratio, which means we need to know how much of the filtrate is actually coming back to the recycle, and we will have to calculate the recycle ratio as recycle divided by fresh feed. So, let us start performing the calculations required. So, just like any material balance problem, the basis would be taken from the information given. So, you have 4500 kilograms per hour of fresh feed entering. So, the basis would be 4500 kilograms per hour. Basis is 4500 kilograms per hour of fresh feed. Now, let us label the terms which we need to calculate. So, let us call the total feed entering the evaporator as M1 and the rate of evaporation as M2 and the feed rate to the crystallizer as M3, and amongst the product leaving we will call the solid crystals, mass of the solid crystals as M4 and the liquid which is accompanying the filter cake as M5 and your recycle stream as M6. Now that we have labeled these streams, let us look at which systems to choose and what balances we can perform. So, for most systems we always start with overall balance. So, we will take the overall system and start writing the balances for the overall system. So, the overall system is taken and we can write the total mass balance and the mass balance for potassium chromate. So, the total mass balance would be 4500 kilograms which is entering would be equal to M2 plus M4 plus M5. So, M2 is the water which is leaving in the form of water vapor, M4 is the potassium chromate crystals leaving the crystallizer and filter, and M5 is the mass of potassium chromate solution which is accompanying the filter cake. We can also write the balance equation for potassium chromate. K2CrO4 balance would be, you have 0.333 times 4500 entering and you have potassium chromate leaving in the form of M4 plus 0.364 times M5. So, we now have two different equations. It has also been given that 95% of the mass of the filter cake is constituted by the crystals. The problem statement gives you that. This means you have M4 equals 0.95 times M4 plus M5. Using these two equations we can calculate the values for M4 and M5. So, M4 would be 1470 kilograms per hour. So, this is the rate of production of potassium chromate crystals, and from here we can also calculate M5 which would be 77.5 kilograms per hour. So, this is the amount of liquid accompanying the filter cake. So, using the total mass balance which we had, we can calculate M2, which is the mass of water vapor which is leaving the evaporator, which is also the rate of evaporation. That value would be 4500 minus 1470 minus 77.5, giving you roughly a value of 2950 kilograms per hour. So, the next thing we need to calculate is the recycle stream and the feed rate for the crystallizer. For doing this, we need to choose appropriate systems. We would not be able to get these values using the overall system. So, what system do we consider? So, we can, for performing these calculations, we could either choose the mixing point plus the evaporator or the crystallizer and filter as the systems. In this case, I have used the crystallizer and filter as the system. Considering the crystallizer and filter as the system, I can write a total mass balance as follows. You have M3 entering and you have M4 plus M5 plus M6 leaving the system. You can also write the water balance for the crystallizer. So, the water balance would be 0.506 times M3 equals 0.636 times M5 plus 0.636 times M6. So, we already know the value for M4 and M5. So, using the values we have, we can calculate M3 and M6. So, from that we get M3, which is the feed rate to the crystallizer, as M3 would be 7200 kilograms per hour, and the calculations will give you an M6 value as 5650 kilograms per hour. So, this is the rate of recycle. Now that we have the rate of recycle and we already know the fresh feed, we can calculate the recycle ratio R as 5650 divided by 4500, which is the fresh feed, giving you a value of roughly 1.26 kilograms per kilogram. So, with this we have calculated all the parameters which have been asked for in the problem. As you saw, the most important thing about performing these calculations was that we had to identify the right system. So, the simple logic we go with is, I use the overall system for the first step and then identify smaller systems for the next steps. So, this works efficiently for the problem statement which we had, simply because we had all the information about the compositions of the streams which are leaving the overall system or entering the overall system. So, if we have the information about compositions of some stream which is crossing the system boundary, then we can actually use that system to perform these calculations. So, drawing the system boundary in a way that we have the streams crossing the system boundary and have the information for these streams will help us in solving these problems in an easier way. In the previous tutorial problem, we looked at a system with recycle but without reaction. We will solve one problem with reactions and recycle. So, this problem has both the reaction and recycle. Have a look at the problem statement. Cyclohexane can be made by the reaction of benzene with hydrogen according to the following reaction. Benzene plus hydrogen forms cyclohexane. From the process shown, determine the ratio of recycled stream to the fresh feed stream if the overall conversion of benzene is 95% and the single pass conversion is 20%. Assume that 20% excess nitrogen is used in the fresh feed and that the composition of recycled stream is 22.74 mole percent benzene and 77.26 mole percent hydrogen. Also calculate the product stream composition. So, in this problem we have been given the overall conversion and the single pass conversion. Do you remember what these are? Overall conversion is the conversion which is obtained when we account for the overall system. So, the system we choose for this would be the overall system, and the amount of reactant which is consumed by within the system divided by the amount of reactant supplied to the system would be the overall conversion. If we were to calculate the single pass conversion, we would account for only the reactor where the reactants are actually passing through the reactor only a single time. Thereby we have a single pass conversion or an once through conversion which has also been given here. So, for this problem we have been told that the single pass conversion is 20% and the overall conversion is 95%. Using these values, let us try to solve this problem. The first step for solving any material balance problem would be identifying the appropriate basis. In this problem there are no flow rates given. This means we can choose any basis. Here I have chosen 100 moles of benzene in the fresh feed. Why have I chosen this? In the problem it has also been given 20% excess of hydrogen is fed along with the fresh feed. This means if I use 100 moles of benzene as the basis, I can calculate the number of moles of hydrogen using this 100 moles as the basis. So, this will give me cleaner numbers. If I were to use 100 moles of fresh feed, then I will end up with more cumbersome numbers which can make the calculations a little more tedious. For this reason, I will be using 100 moles of benzene in the fresh feed as the basis for this problem. So, let us start solving the problem. Basis is 100 moles of benzene in fresh feed. Looking at the stoichiometry, we know that 1 mole of benzene requires 3 moles of hydrogen. So, 100 moles of benzene would require 300 moles of hydrogen. We have been told that hydrogen is supplied at 20% excess. This means hydrogen supplied would be equal to 300 times 1.2 giving you 360 moles. So, the total fresh feed we have would be 460 moles. The overall conversion has been given as 90%. So, overall conversion is equal to 95%, sorry, not 90%, 95%. So, now for the overall system we can write species balances using the moles that we have. So, if we were to take the overall system, we can write a benzene balance. So, it would be input minus output plus generation minus consumption equals accumulation. At steady state there is no accumulation, benzene is not generated because it is a reactant. However, you have input, output and consumption. So, your output would be equal to input minus consumption. We have already used the basis for input as 100 moles of benzene. And we now need to calculate the consumption. We have been told that 95% of the benzene entering is converted by the overall process, which means consumption would be 95% of whatever is entering, which is 100, giving you 95 moles being consumed. Thereby your output would be 5 moles of benzene. So, your value for NPBZ here would be 5 moles. Now that we have the information about the benzene, we can write balances for hydrogen to calculate the amount of hydrogen in the product. So, let us write the balance for hydrogen. Again hydrogen balance would be input minus output plus generation minus consumption equals accumulation. No accumulation at steady state, no generation for the reactant. So, your output is basically input minus consumption. We know that input is 360 moles. We know that 95 moles of benzene is consumed. This means using stoichiometry, for 95 moles of benzene consumed, there would have been 3 times 95 moles of hydrogen which is consumed. So, consumption for hydrogen would be 3 times 95, which is 285 moles. So, from this we can calculate the output, which would be N hydrogen in the product as 360 minus 285 giving you a value of 75 moles. Similarly, we can write a balance for cyclohexane to calculate the amount of cyclohexane in the product. So, your cyclohexane balance C6H12 balance would be input minus output plus generation minus consumption equals accumulation. At steady state there will not be any accumulation, as this is a product there is no consumption of cyclohexane. So, you do not have any cyclohexane entering, so your input is also equal to 0. So, which means your output is basically equal to generation. Using the stoichiometry, we know that for every mole of benzene consumed there is 1 mole of cyclohexane produced. So, this implies 95 moles of cyclohexane would have been produced for 95 moles of benzene which was consumed. Therefore, generation would be equal to 95 moles. So, the output in the product which is NC6 the output in the product so the amount of cyclohexane in the product which is NPC6H12 would be equal to 95 moles. Now that we have all the information about the components in the product stream, we can calculate the molar composition of each of these, and these fractions can be calculated. I would leave that out as an exercise for you. The other important information which has been asked in the problem is to calculate the recycle ratio. Now, for identifying the recycle ratio, we need to choose a system where the recycle stream crosses the system boundary. So, what would be an appropriate system that we can choose? From the problem, we have information about the single pass conversion, and based on the calculations we have done, we have the information about the product stream. Hence, choosing your reactor and separator as a system would help you use the single pass conversion and also use the values we have calculated for products to finally calculate the recycle stream. Let us try to write the balance equation for this particular system. If we were to write a benzene balance for this system, the benzene balance would be input minus output plus generation minus consumption equals accumulation. At steady state there is no accumulation, benzene is being consumed, not generated. You have benzene leaving and entering the system. So, your equation is this. Now, you have benzene entering in the form of the total feed. So, the total feed basically is 100 moles of benzene in the fresh feed plus 0.2274 times R, which is the number of moles of benzene in the recycle stream. This together forms the amount of benzene in the gross feed, and this minus the amount of benzene leaving the system would be the benzene which is unreacted leaving through the product, which is 5 moles plus 0.2274 times R, which is the benzene leaving the system through the recycle stream, and the amount of benzene consumed would be based on the single pass conversion. Single pass conversion has been given as 20%. So, 20% of the benzene entering into the system would have been converted. So, using that we can calculate the consumption as 0.2 times the amount of benzene entering, which is 100 plus 0.2274 R. So, this is equal to 0. So, using this equation we can calculate the value for R as 1649 moles. Now that we have the number of moles of the recycle stream and we already know the number of moles of the fresh feed, we can calculate the recycle ratio as recycle ratio would be equal to R divided by F, which is 1649 divided by 460, giving you a value of 3.58. So, with this we have calculated the product stream composition, the components in the product stream, and also the recycle ratio. With this we come to the end of this problem and to the end of this tutorial session. I hope you were able to understand whatever we have discussed here, and you would be able to perform these calculations with ease. we will perform more calculations and more example problems for material balances to make sure that we have a full understanding of whatever we have discussed till now. In the next lecture, we will talk about bypass and purge. These are two new concepts which are crucial with respect to recycle. So, we will look at these systems and see how material balances can be performed for these systems. Thank you.